All right, let's talk about quantum computing in 2026, because the game has completely changed. This isn't just about abstract theory anymore. We have officially entered a new, powerful, and intensely practical era. You know, for the longest time, this was the big question in tech circles. The whole world was focused on this one monumental challenge. Could we even build a working quantum computer? It honestly felt like something straight out of science fiction. Well, that question, it's been answered. The race has totally shifted. It's not about just building these incredible machines anymore. Now it's all about making them stable, making them consistent. Reliability, that is the new frontier. And this new phase, it's really all about mastering one single concept: quantum error correction. This is the key. It's the thing that's finally going to unlock the real-world industrial value that quantum computing has been promising for decades. At the absolute heart of this race for reliability is something called the logical qubit. So instead of trying to rely on one single, super fragile physical qubit, the idea is to group a whole bunch of them together. They basically work as a team to create one ultra-stable, error-resistant logical qubit. This idea right here, this is the foundation of the entire resilient quantum era. So who's actually leading this race? Well, there are three main contenders, and what's really fascinating is that each of them is taking a radically different approach to solving this problem. First up, you've got Google. They're chasing raw processing power with these superconducting chips that have to be kept colder than deep space. Then you have Microsoft and Quantinuum betting everything on stability with a completely different kind of technology called trapped ions, using lasers to hold individual atoms. And finally, there's IBM. They're going for a really clever, modular, Lego-style approach, linking smaller processors together. So it's this high-stakes competition between three fundamentally different ideas about how to build the future. And if you want to understand what raw power really means, just look at Google's Willow chip. It did a calculation in under 5 minutes that would take the world's fastest supercomputer 10 septillion years. Let me just say that again. 10 septillion years. That's a 1 with 25 zeros after it. I mean, the scale of that is just staggering. Now, while Google chases speed, Microsoft and Quantinuum are laser-focused on reliability. They've already shown logical qubits with an error rate 800 times lower than the physical ones they're made of. And get this, their Helios system is the first machine that can actually find its own errors, fix them on the fly, and just keep on going without crashing. That is a massive, massive step forward. And this perfectly shows IBM's modular strategy with their Kookaburra processor. Instead of trying to solve one huge problem on one giant chip, they use this technique called circuit knitting. It's brilliant, really. They just break the problem into smaller chunks, solve those pieces on separate processors, and then cleverly stitch all the results back together at the end. So this ability to solve huge, complex problems is, well, it's revolutionary. But that incredible power comes with a dark side, an immediate and urgent challenge that actually impacts every single one of us: our digital security. The very same power that could help us solve humanity's greatest problems could also be used to shatter the digital security we all rely on every day, for banking, for communication, for literally everything we do online. It basically signals the death of encryption as we know it. And don't think for a second this is some hypothetical, far-off threat. It's happening right now. It's an attack called Harvest Now, Decrypt Later. Adversaries are stealing massive amounts of encrypted data today, and they're just storing it. They're waiting, knowing that in just a few years they'll have the quantum keys to unlock it all. This is so real that governments and banks are in a frantic race to upgrade their security. And yeah, the clock is absolutely ticking. New quantum-safe standards from NIST already became mandatory in early 2026. The bigger goal, especially for banks and financial institutions, is to be fully quantum-safe by 2030. Why 2030? Well, that's the window when most experts predict our current encryption could be cracked wide open. Okay, but enough of this scary stuff. Beyond the threats, this new era of resilient quantum computing is already being used as an incredible tool for good. It's literally becoming science's new superpower. And we're already seeing the first real-world applications pop up. At St. Jude Children's Research Hospital, they're using these machines to simulate how a potential drug might click into a cancer cell, which could drastically speed up drug discovery. And car makers like BMW and Mercedes-Benz, they're using them to simulate new molecules for batteries, all in the hopes of giving electric vehicles way more range. So what happens next? Well, the road to 2030 is actually pretty clearly mapped out, and each milestone along the way is set to unlock some incredible new capabilities that are going to shake up major global industries.
The progression here is just fascinating to watch. First, perfecting that circuit knitting technique will help streamline global logistics and flight paths. Then, once we reach 100 stable logical qubits, that will unlock complex molecular simulations, helping us design new catalysts for carbon capture. And finally, the Holy Grail, achieving full fault tolerance. That could lead to one of the biggest dreams in science, discovering room temperature superconductors.
So, you see, we're no longer asking if quantum computing will change the world. The question now is how and when. The race for reliability is on, and the solutions it's going to unlock, from medicine to materials to global security, are going to completely reshape our future. So the only real question left is, where do we point this incredible new power first?